like to do, here's kind of our plan. We've been a little bit interrupted with trying to finish up that test, and people have done, I'm really, really happy with where we are. It seems like people are getting that stuff. It's hard stuff. It's, it takes a little while to kind of get used to it, but I know it was a long process, but you will be glad that I think that you took the time to figure it out now, because we use it all here. Right? We're going to go away from it for a little bit now, but it won't be long, and we'll be looking at vector resolution again. The good news is we get to look at it in the context of some really interesting kinds of problems as we move into bigger and better stuff. But let's get back to sort of what we were talking about last week. Okay, I gave you a book assignment. I don't know if I haven't mentioned this. I think I just did, but if I didn't, it's on the Moodle calendar for physics. I think I put it on there as being due Tuesday night, which doesn't make any sense because it's not a Moodle assignment. So what that means, I guess, is Wednesday in class we'll go through it. Okay, we'll take some time. I do want to start a lab too. We're getting to a point now. We haven't really been able to do any labs that we could have done to this point. Would have been pretty dark. But now we're getting to a point where we can start to look at motion a little bit. We've got some good equipment that allows us to investigate motion. I want to get used to that. It'll be kind of a learning experience for all of us here. I've used this equipment in the past, a long time ago, but there's been some changes to it, and so the first lab will be a learning experience for me also, with how to best utilize the equipment we've got. It's excellent equipment. We were able to hook up the sensors to computers, and we can take the data in real time into the Logger Pro is the Vernier software, where we can actually import the data and put it into a position time graph or a velocity time graph, and does some really cool stuff. Additionally, there are some new bells and whistles. I have to make sure all this stuff is installed properly, but we can even have Chromebooks in there and export the data from a lab station. Say you guys are working like a group of 4 or 5, or in this class maybe a little smaller. You can export the data from the computer, I believe, out to the Chromebook, so everybody can have the data right in front of them to work with. Yeah.
In calculus, in honors chemistry, we did that.
Okay.
We tried those.
Okay.
Both of them.
And it worked?
It worked.
Okay, good. So you've seen it done, then maybe you can help me with it.
It was last year.
Yeah, well, it can't be that hard. I mean, I'll look at it.
They're pretty in the middle of the year, so.
Gotcha. Gotcha. Well, we'll get it figured out, and then we'll have the access to that all year. There's some really cool equipment in there. We're going to be using the motion sensors, which are ultrasonic motion sensors, and so you'll set them up and just give you kind of an idea. And then I'll probably take you through a couple just introductory labs to get used to it. One of them looks kind of fun. It's where you have to one person, each person can take a try at this. You've got to try to walk in such a way that you can make your motion diagram match like a pattern. I'm going to say, okay, everybody try to get this one. And then you got to try to get that motion diagram based on, you can kind of see, you can look at the computer and kind of see what it's doing and get an idea. But there's that one, and then we'll do some stuff with the carts, where we can tilt the plane so the carts accelerate, and we'll investigate some motion of those really good motion carts on the tracks, and it'll be fun. You'll like it. So, but to get there, we got to maybe get through just a little bit more of this stuff. On the assignment, there's I think question 11. Everyone's had a chance to work on this a little bit. The book assignment, hopefully. Question 11, it's in several parts. Question 11 comes from the last of the 3 groups of problems on the assignment, but I think it's a good one to look at. There are some other questions that deal with a lot of kind of the stuff that we were going through last week, a lot of position time graphs, right? And if you have any other questions on those, we can certainly look at one. But let's start off with 11. 11 is summarized up on the board. So we've got a car starts with 2 times 10 to the 2 meters west of a town square and moves with constant velocity of 15 meters per second eastward. Choose a coordinate system in which the x-axis points east and the origin is at the town square. So we can do that real quick. So what's that look like for us? This is just motion on a line. So isn't this going to be That's the axis that we're interested in. This is the positive x or east direction. We'll let the origin be right there, and that's going to be the town square, right? Okay, so they want us to do some stuff with this. First thing they want us to do is they want us to write the equation that represents the motion of the car. Well, we only have one equation in this section. Now, this is the first of, and maybe the easiest, of a series of kinematics equations that we're going to introduce in this chapter, and we'll use a lot more next chapter. This one, and it's on page 88. This one, the book labels position with constant velocity, which makes sense. Here's what it says. It says that D, which stands for what? Well, position, right? In this book, it's position. Usually, and you're likely to see like in a college physics class, usually the variable S is used for position for some reason. Okay, so what do those things mean? What is D naught or D sub 0, do you suppose? Yeah, good. That's the 0 means when we start the stopwatch, right? That's time 0. So that's our, what might we, starting position, or what's the other word we use sometimes? Oh, I think I almost heard it. Initial, there we go. Okay, there we go. Good. So,
I was like,
that's initial position. What's the V? Velocity, sure. What's the T? And you already told me that this is position. I'd like to add something to this, though. What does that mean, you suppose? Is that D times T? Say it again.
Distance at a time.
Okay, yeah, what we'd say is distance as a function of time, or position as a function of time. Or we could just say like D of T, right? That's like in math when we use function notation and we say f of x. Doesn't mean f times x. It means the function f that's going to be written in terms of an equation involving the independent variable x, right? So this is just preparing us for the fact that we're going to be calculating position with some expression that involves the variable t, right? Okay, so now let's take, this is real similar to what we're doing in calculus right now, those who are in calculus, right? We're starting with a basic template, and then we're just going to get more specific, right? So let's get more specific. Now, here's the situation as described in the problem. Let's extract some information. Somebody tell me something I can add to this equation. Okay, good. So, yeah, this right here. So this says, let's color code this. So 2.0 times 10 to the 2 meters west of the town square. So what does that become then? Initial position. Okay, that's initial position. So what is my initial position then? I do put negative, don't I? Because we're dealing with vectors here, right? And it's west of, there's the town square. It'd be over here somewhere, wouldn't it? Right? We could call that, if we labeled that, that's initial position, right? So it's negative 200 meters, isn't it? Okay? Something else. Oh, okay, the velocity. Yeah, we have a velocity of 15 meters per second eastward. What's that? Positive 15, because it's moving in the positive direction. So V equals 15 meters per second. Good. And so now I can plug that stuff in, and I can come up with a specific equation for the position of the car, right? So what do we get when we do that? All this stuff gives us D of T equals, what was our initial position? Negative 200 meters plus 15 meters per second times t is our independent variable. Make sense? Okay. And so now all we'd have to do is just plug in values of t, and this is the physics god's way of telling us where the position will be. We commune with our physics gods through equations, and they'll give us the answers if we ask the right questions. I mean, we use the right equations and we put the right numbers into them, the right values, right? So what do they want to know then? They want to know in part B, where will the car be 10.0 minutes later? So can I put a 10 in for t? Okay, it has to be in seconds. Good. Right. So, and I want to point something out here. What we always want to do, whenever we possibly can, we always want to be in terms of MKS units. Those are our standard units. Those are units built on meters, kilograms, and seconds. Right? And what you'll be able to do maybe a little bit later. At first, I want you to resist this temptation, but a little bit later, as you get better and better at this, as long as you are making sure that all of the quantities involved are MKS units, you could even suppress the units and just know that when you're done, the answer is going to be in terms of the appropriate standard MKS unit, right? But for now, let's not do that. There's a reason for it. You'll see in a second. So we've got to convert then, don't we? We've got to convert the 10 minutes into seconds. Now in the book, they give it some goofy name here. They call it the factor label method of unit conversion. Never heard that before, but I suppose it's probably accurate. What does that mean? All it is this. So if we're going to try to convert 10 minutes into seconds, this is what I call multiplying by a changer. That's how I've always taught it. So whenever we want to change from one unit to the next, we have to multiply by a changer. All the changer is literally just it's a ratio. It's going to be a factor that involves a ratio of 2 units, right? So I think we maybe talked a little bit about this before. What I would always do with this is I would always start off with the units. If we want to convert from minutes to seconds, that tells us right away which unit has to be on top and which has to be on the bottom. So which is it? Seconds on top, good. And then the minutes on the bottom. And both of those are important. We know that the minutes have to be on the bottom because we need to be able to cancel the minutes. We cancel units just like we cancel variables, right? In algebra, we can cancel like variables top and bottom, right, if they're factors. Same thing with units. So the minutes will cancel. There's an invisible 1 on the bottom there, isn't there, right? So now what we want to do. Now we need to say equivalent quantities on the top and the bottom. Think about this for a second mathematically. We're trying to take a unit of time, a quantity of time, right, 10 minutes, and we want to change the units. Are we changing the duration of the interval? No. We want it to be the same length of time, just expressed in different units, right? If we change the duration of the period of time, we would be fundamentally changing the problem and getting a wrong answer. So that means if we don't want to change a value, we're just changing the units, what's the only number we can multiply by and not change something? 1, right? A fraction that's equal to 1 has the same value in the numerator and the denominator, right? 10 over 10 is 1. 13 over 13 is 1. So in this case, we need to say a unit of time in the top that's exactly equal to the unit of time in the bottom. There's an infinite number of possible choices we could pick. I could pick 2.5 minutes on the bottom and 150 seconds on the top, but that's not very convenient. We want to pick an easy one. What's an easy one? Yeah, 1 minute and 60 seconds. Whenever you can express a conversion in terms of using a 1 and something else, yeah, do that. And that's the great thing about metric. You always can. With anything metric, and time isn't metric, unfortunately, but with any metric quantity, you can always pick one big one and some power of 10 smaller ones that goes with that, right? Does that make sense, though, what we've done? Okay, so then the minutes cancel. If we look across numerically, all we do is we just multiply straight across. And we could have a whole bunch of changers up here, right? What if we were trying to, well, we'll look at another quick example after this. So if we multiply straight across, we just get 10 times 60 is 600 over 1. is just 600, and then the units are seconds. And that's it, right? Real quick, did we do an example in here of going from like miles per hour to kilometers per second or something? Okay, let's do one of those, just so we've, I think it wouldn't be bad. Real quick, just to get a little additional practice with this. What if we want to go from, let's say, 45 miles per hour into meters per second? Okay, so we've got to multiply through some series of changers to change the miles on top to meters on top and the hours on bottom to seconds on bottom, right? We could certainly do this using some shortcuts, but I'm going to purposely just take some really easy changers. So let's start off going from miles to meters. Now, I know that there's probably a better conversion in the back of your book, and by the way, that's where they are. If you look in the very back of your book, useful conversion gives you a whole bunch on that back cover. But the one I always remember is this. I know that at that a 10K race is roughly 6.2 miles. So that's how I always remember to convert, anything involving like miles or feet or anything into meters or centimeters. I always go through that one conversion. So then we could write that as what? I want to go from miles to kilometers. So kilometers are on the top, right? Miles are on the bottom. And you might have a much better conversion for that. That's just the one I remember. So now what's an equal quantity expressed in kilometers and miles? We said 10 kilometers was 6.2 miles, right? And so that's going to cancel the miles, leaving me with kilometers. I need to get to meters. And so what's going to be the conversion to go from kilometers to meters? I got to cancel the kilometers and leave myself with meters. What's an easy conversion here? 1 kilometer is 1,000 meters. And so now we're good, right? The kilometers cancel. I've got my meters on top, which is what I want. Now I got to deal with the time unit on the bottom. So I got to go from hours to seconds. Okay, well, I'm going to do that in 2 steps. I'm going to go from hours to minutes and then minutes to seconds. So we probably could just do it in 1. So what goes on top then? What unit? Hours. Minutes on the bottom. What are good numbers to use that relate hours to minutes? 1 and 60. Good. And then that cancels the hours on the bottom, and now we're left with minutes on the bottom. We're closer, but we're still not there. So we'll multiply by, we want to have minutes on the top to cancel and seconds on the bottom. And then we just get 1 and 60 again, right? And so the minutes cancel, and now we got what we want. Seconds on the bottom, meters on the top, and we just multiply straight across and get an answer. So somebody on your calculator, or me on my calculator, how about? We'll just do that. Does that make sense what we're doing? And this is a really handy way to do it. You can change, really this will never fail you. As long as you can find some link between the units, some conversion factor, this will always work. All right, so let's do this. Okay, so let's make a fraction template. How about on the top we've got the numbers 45 times 10 times 1,000. I think that's it, isn't it? Yeah, and then just times 1 times 1. So on the bottom we've got 6.2 times 1 we can skip, times 60 times 60. Gives us 20.16. So let's just say we can keep, how many sig figs did we have? I think we only had 2. I said 45. So it would be about roughly 20. So 45 miles per hour is roughly 20 meters per second. Okay, make sense? Okay. Okay, so going back to our problem though. So we actually calculated the 600 seconds for a reason, didn't we? We were in the middle of doing a problem. So we wanted to be able to where were we? Oh, it was up on top. There it was. Okay. Yes, we wanted to be able to figure out how far we'd traveled after 600 seconds. So we've got our equation then right here, right? We're just going to calculate position at 600 seconds. And that's going to give me negative 200 meters plus 15 meters per second times 600 seconds. Okay, notice what happens to the units. The seconds cancel there, and I get back negative 200 meters plus, what, 9,000?
Yeah.
So negative 200 plus 9,000 is 8,800 meters, right? So that's our answer. After 10 minutes, we would have traveled 8,800 meters, 8.8 kilometers. Okay? There's another part to this. They want to know when will the car reach the town square? This is, to me, a much better, this is kind of more interesting question. So how are we going to do that? How are we going to interpret that one? When, I'm going to grab just the stuff on top here. About stuff. Just grab that stuff there. There we go. So how are we going to do that? We want to determine how long it takes us to get from our starting position to the town square. So once again, we're going to be using this equation, right? Our position with constant velocity equation. Only what are we going to input this time? Initial position stays the same, right? Velocity stays the same, but we're not inputting a time. We're trying to solve for a time. So what else do we know? We're trying to get there, right? I don't know how long it takes us to get there. So we actually, if we're asking a question about how long it takes, we're going to end up solving for which variable in that equation? Time. Yeah, so time has got to be the unknown, doesn't it? Everything else we should be able to plug in. But what are we missing? We got initial position accounted for. We got velocity accounted for. What about position? What position corresponds to the town square? 0. Yeah, that's the origin, isn't it? That's what they told us to define as the origin. So now we've got 0 there. So in addition to this other stuff we had up here, we've also got d equals 0 meters, right? And so this equation then becomes 0 meters equals negative 200 meters plus 15 meters per second times t. T is the only unknown, so that's what we have to isolate, right? When we solve for a variable, we isolate. What are the 2 steps in order to get t by itself? Okay, add 200, and then divide by 15, right? Okay, so what happens when we do that? So we end up with then t all by itself on one side, and on the other side, we're going to get positive 200, right? 200 meters divided by 15 meters per second. Okay, so that's going to give us, numerically, we're going to get back 13.3 repeating, so 13 1/3. What about the units? Now what's going to happen with the units? meters divided by meters per second. We said we treat units just like variables. Well, what do you do when you divide by a fraction? Okay, flip and multiply. Multiply by the reciprocal. So the units we're going to get then are going to be meters times the reciprocal of meters per second. Does that work? Meters times seconds per meter. What is there any? Yeah, there's some cancellation, isn't there? The meters cancel, and we just end up getting seconds. And so that tells us we're on the right track, doesn't it? That's why I would encourage you to keep the units in for now, because this is called dimensional analysis. And if the units work out, then that's a good sign that, probably we're on the right track. It's not a guarantee, but if they come out wrong, we know we're on the wrong track, right? So rounded back, how many sig figs can we keep? It looks like just 2, doesn't it? Got 2, 2, yeah, so what's this gonna be then? 13 seconds is the time it takes to get to the town square. Okay, make sense? Okay, got another challenge for you. I'd like you to try, I want you to, come on now. Okay, I want you to draw a position time graph for me with these characteristics. So say we're talking about a person. At point A is going to be, we'll label these points on the position time graph. So point A is when we start the stopwatch. The person stands still for some short time until time B. At time B, the person accelerates to high speed, begins accelerating to high speed. At C, they're done accelerating and they maintain high speed between C and D. At D, they start to decelerate to a lower speed. And then at E, they begin to just maintain that low speed until F. That's when we'll stop. So you obviously can't make this precise because I haven't given you any numbers, right? But I just want to I want to see just what the shape of that graph might look like. Let's have a look. So let's assume we're starting at the origin. How about? I didn't mean to say that, but let's assume we're starting there. So that's point A. What does the trip from A to B look like? Yeah, it's just going to be pretty boring. Just going to look like that, isn't it? Right? The position is not changing. Okay. From B to C. Now accelerating, so I'm picking up speed to some high speed. So what's a high speed going to look like? Good, it's going to be a steep slope, isn't it? So I've got to gradually increase, uniformly increase from 0 slope, right? And keep in mind, remember what we said about position time graphs. The slope of the graph tells us the instantaneous velocity, right? So we got to go from no velocity to pretty high velocity. What's that going to look like? Okay, I'm seeing some people doing this kind of thing. Yeah, it's going to go something like, maybe like that, isn't it? So there's C. So we're going from a low velocity to a pretty high velocity. And then from C to D, if we're going to maintain that high speed, what's that going to look like? Yeah, okay, we're just, whatever that slope was, we're just going to keep that slope for a while up to point D, right? Okay. Now, D, I use the word, the ugly word. I use decelerate to a low speed. Decelerate just means slow down, right? So if I'm decelerating to a low speed, What is that gonna look like? Yeah, I've gotta go from a steep slope to a not so steep slope. So maybe something like that. And there's E, and then from E to F, we maintain that low speed. So maybe something like that. Does that look right to you? Okay, good. Okay, we'll hold that one in reserve. We might come back to this. I don't know if we're gonna have time. Oh boy, we're running out of time. Mondays are just, I don't like, Mondays aren't long enough for us. We get enough good stuff done. Last step I wanna take, I wanna remind you about something that we just started talking about last week. This will get us ready for tomorrow. So let's take a position time graph. We're gonna start with a really simple one. Tomorrow we'll get into some more complex ones. Take a position time graph. Holy smokes, what's going on? Position time graph, and let's turn it into a velocity time graph. So here's my position time graph. Okay, there's position time. Now think for a second, what's this gonna look like in terms of a velocity time graph? And the part I wanna remind you about, this is really good for calculus too. Remember that the value of an object's velocity at any moment in time corresponds to the slope of the object's position time graph, right? The value of the velocity time graph corresponds to the slope of the position time graph. So what can you tell me about the part of this motion from A to B? What can you tell me about the slope there? It's constant and positive, so therefore what can you tell me about the velocity between A and B? Constant and positive, isn't it? Exactly, constant and positive. So it would just look something like maybe this, right? Agreed?
Yes.
Okay, what can you tell me about the part from B to C?
Still.
The slope. The slope would be 0, right? So even though the position is positive, the slope of the position time graph is 0. And so the velocity would be 0, right? Okay, what about the part from C down to D? Constant and negative. Okay, so on the velocity time graph, where's that going to be? Yeah, it's going to be below the t-axis, right? The negative y-axis is down here, negative y values, so it looks like that. Now, for you calculus types, I think I even mentioned this maybe on Friday, but those would have to be open circles. And why is that, calculus types? Say it again. Because we can't have a derivative at those places. Why not?
Because the slope wouldn't be.
Right. Well, the derivative doesn't exist, right? And the slope is, and slope means derivative, and it's because those are what kinds of features on the curve? No. We don't have derivatives at sharp corners. Yeah. We don't have derivatives at sharp corners, and so the velocity, which is the derivative, and if you're not in calculus, just ignore this. But we would technically want to have open circles there. Makes sense in a way, doesn't it? Because how could you possibly go from some constant positive velocity to 0 velocity instantly? That's not physically possible, right? And so that's kind of the physics god's way of telling us, whoa, that's a little pokey. We have to have open circles there. Okay, very good.